Alright, let's go. I need the fan. Okay. Okie doke. Continuing numeric conversion. Numeric promotions, we're implicitly converting a type of the same type. So a floating point to a floating point, or an integral to an integral. Integral not meaning characters and booleans, just meaning integer types. So like a fucking unsigned int or an integer 16-bit, that kind of shit. Of course I fucking touched the lens, great. Course type conversion is a fucking boolean to an integer, or a float to a boolean, or a boolean to an integer, integer to a boolean to a fucking, or an integer to a long, because it's not for efficiency purposes. A float to not a double but a long double. Excuse me, a double to a long double to a double. Basically, numerical conversions that aren't for efficiency purposes. They're just to convert shit. Okie doke. Let's go. Hour and a half begins now. A little late, but is what it is. Okie doke. Yep, we had value preserved, so we had safe and unsafe conversions. And safe conversions being like, I guess I'll type more of this shit out instead of talking it out as much. So like, int x is 5, and then we say int long int y is assigned. And actually in this case we can do values value, or not value, brace initialization like this, because long ints can contain all values of ints. But if we instead did this guy, and then int x is copy initialized the value of y. In this case, but usually long int to int conversions would be narrowing. So if we did brace initialization like this, we get a warning because we have a narrowing conversion from a long int to an int. Ints can't hold all values that long ints have. But what? What's happening here? What are you talking about? Oh, okay, doesn't matter. So, and actually I think maybe it wasn't even an issue there because the value was safe. So a value preserving conversion would be an int to a long int to an int is still value preserving because we have a safe value in this case. So what, there are safe and unsafe conversions, value preserving and non-value preserving. So like in this case it's value preserving, but if this was 5, let's say -5, and we said unsigned int 5, or unsigned int x, well, this is a non-value preserving function, so we're not, and actually we're also potentially losing data. Maybe not in this case because, yeah, I guess we have more zeros, so we are actually losing data here. Because we have a long int that has some, like whatever, 8 bytes, I guess. If a regular int is 4, and we usually double when we add long, I think. So if we're going to an unsigned int, not only are we losing data, which isn't terrible here, but we're going from -5, which is a signed value, into an unsigned value, which means we're going to get 4 less than whatever the maximum value of an unsigned int is. So like, I don't know, 4 less than like 2.15 billion or something like that, or 4.3 maybe, or 2.3, something in that area. So the point is, if we could have that, we could also have an unsigned int value called variable called x, and it's like some big ass number value larger than what an int can hold, because an integer's memory is split on both sides, the signed and unsigned sides. And now if we have int y is now x, sure, we're not losing data, 4 bytes, 4 bytes. However, the value might be incorrect due to wraparound. Let's just assume that it is. Let's assume that this can be held by an unsigned int, but not by y. Well, we'd say, oh, the value is too positive. It's more positive. I'm doing the yawning thing again. It's annoying. It's so positive that we wrap around and then go up into the negative. So this is probably, y is probably a negative value in this case. And see, these are reinterpretive. Why are they called reinterpretive? Yeah. So value preserving ones are by default when they're okay. So these are safe conversions. Gotcha. And if a value is able to be, or well, let's see. So the opposite of a value preserving function or a conversion, so like where we have an int that's 5 and we're converting it to a long that is something larger. If we then convert it back, we know that the one-way conversion was already safe, therefore the other way has to be safe. For interpretive conversions, it's not necessarily the case, because we take -5 from an integer, we convert it to an unsigned integer, now it's a giant positive number, and then when we convert it back, it'll wrap around, and maybe we get a very negative value now because of wraparound. So we went from a small negative number to a large negative number through the second conversion. So reinterpretive, basically standard ass unsafe one. But we also have more. Lossy, where data could be lost. So double to an int. Okay. So reinterpretive ones are no data loss. It's just that the value is changing. So they're safe, the value isn't changing, and there's no data loss. And then there's reinterpretive where there's no data loss still, but the value is changing. And then there's lossy where there's data loss. And if we're talking lossy, seems like naturally we can also have a different value as well. We have a lot of memory for this large ass number in a long. Convert that guy to an int. It's the same thing, too much memory for it. The value is so positive that the integer can't hold it, so it wraps around. We lose. And we not only lose data, but we also change the value. Yeah, so we don't necessarily want... maybe it's not great, at least when working with arrays, to leave treat warnings as errors enabled. Because that means whenever we try and reference later elements in an array by using negative integers, well, the index of an array is an unsigned integer, seems like the data type, which means we would be converting from an assigned integer to an unsigned integer, meaning that that conversion would flag, just like if we had here. Unsigned and signed mismatch. And regardless, the value could be 4 and it's okay. However, we still have this. So we would need to do like a static cast to an int. Or I guess I could do static cast to an int x. In order to explicitly say, hey, it's okay. We have converted this somewhere, and the return value of that is an integer, so now there is no issue. Everything has gone through. It's not being implicitly converted. So this is the implicit conversion warning. Yes. Okay. So if we did -1 as an integer, and converted that to an unsigned integer, it would be the largest possible value for the unsigned int. And if we convert that back to an integer, the maximum value of an unsigned int is twice, basically twice. Well, it seems like one less technically. Technically, in terms of number, it is one less than twice the maximum size of an integer. So if we convert back to an integer, we would wrap around. The value would be too large, so we would wrap around and it would count all the way up to 0, which is half. Actually, hold on. In this case, if we're at -1, we're at the largest possible value, which is 1 less than twice the value. So it seems like we don't actually count up to 0, we count up to 1 less than 0. Trying to, I guess I'll do paint on it, that's fine. So we could say 0 max, and then 0 minimum to max. Okie doke. This is unsigned int, this is a signed int. If we pass -1 here, it's too small, it's out of range, So we go all the way up to the top. We wrap around, so it goes too small, therefore we go to max. So we get whatever the maximum value is. And then if we go back to a signed integer, we say, hey, out of range. So we count all the way back down. And it's actually, how much further is it out of range? Well, this is 2 times x, and this is x. And x is memory, or number of bytes. So this is a regular fucking, actually, 2 times the memory of the positive. So this is 4 bytes here, but this is 2 bytes here and 2 bytes here. So we're 2 bytes too high. So we start at the bottom now. We wrap around. So we wrap around for the first number and we count all the way back up. And the first wraparound is the first number, which means we have 1 less than whatever the max is. So we actually go back to -1. Don't need to save this. Okay, so it seems like it is actually value preserving. So if we do a reinterpretive, the value is different for one conversion, but if we convert back because there isn't a data loss, it's okay. It's not a long where we're converting it to an int and there isn't room, so it gets some wacky value, and then we convert it back, and then it fits within a long, so it's smaller. So it went from a huge number, converted, it made it small, and then converted, and it stayed small. Instead, for reinterpretive, we have like an unsigned int to an int, or an int to an unsigned int. We have we have a huge number, and it's converted over to an int, So a long convert, oh, not a long, so it's data loss, but a big unsigned int number converted into into a signed int. If that number is huge, it's too high. We count up through however too high we are. Let me see. So the maximum, if we had the maximum value of an unsigned int, converted it to an int, it's too large, so we count, let's see. So we count all the way up through 0, and then we count all the way up to the top, so we get a smaller number. But then wouldn't the conversion back actually be weird? Like, I get the -1 part to be the huge number, and then we count back. But if we started with a huge number and we count, wait, I actually think it's the same result. It's the maximum for an unsigned int, so it counts. Yeah, that's it. I was overestimating it. I was thinking it was going to count all the way from the bottom for some reason. No. So if we have, let's say the max for an unsigned int is 2 billion, the max for an int is 1 billion. So we pass 2 billion to the int. Oh, the int says, okay, we're at 1 billion, 1 billion and 1. Oh, it's too large. We go all the way down to -1 billion. Oh, we still have 999 million, blah, 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 whatever, to count up. So we're at the minimum, and we count up that value. And in that case, the numbers would work out to be -1 for the int. Because the wraparound is 1, it costs 1, and then we count all the way up to 0, -1, because we've already counted down 1, so we don't have an entire maximum or minimum value to 0. We have the entire minimum value to 0 -1, because we had to count 1 off to get down to the minimum value. And then that would bring us up to -1 that we would count up through. And then if we converted the -1 back to the unsigned int, then it would give us the maximum value for an unsigned int. So yes, converting back to the source for a reinterpretive conversion actually does preserve the value. Okay, because there's no data loss. But if there's data loss, then we're going from something that has, it's like we have a large piece of cheese and we put it in a small cheese grater and we lose a bunch of excess. And then or like I put a large piece of wood on a table and I cut off the excess, and then I have a big ass table and a big ass piece of wood that spans the whole thing. I take that whole big ass piece of wood and I put it on my small table, and then the excess falls off the table. Now we have a smaller piece of wood. If I put that back on the big table, we have lost data, so the length doesn't encompass the same amount of the first table because there's less data. We have cut it off. The act of converting it lost data, which is why they're called lossy conversions, as opposed to the safe value preserving conversions, the reinterpretive conversion, and unsafe, at least for an initial conversion, reinterpretive conversions. So lossy loses data, which is why when we convert, we get a smaller memory number, and when we convert back, well, we know that there's no loss of data on the conversion back because the source was larger in terms of memory than the target. So if the source becomes the target, well, it can fit whatever we've got because 1, it started with it, and 2, we actually cut information off of what it started with. So of course it can fit it. It's got extra room now, which means it's got extra room. The value is not the same. We pass the maximum value of a long to an int, we lose the excess. And then we end up with just a regular ass int value. And then we pass the int value back to a long. Well, the long doesn't see, oh, the int value's at a range, let's wrap back around. No, it doesn't see that. There's no conversion like that. It just takes the smaller number and has it as is because it can fit it already. Versus the reinterpretive, where conversions either way, there's no data loss. Both ways cause wraparound in the value conversions. Yep. So reinterpretive conversions do not lose data. So if we did if we had an int x and it's -1, and then we had unsigned int y is x, and then we just output y. Well, there's an unsigned mismatch here. So I think we can make this okay by just doing a static cast to an int. Well, no. Oh, oops. This should be to an unsigned, to an unsigned int. So we had -1, and we converted it to an unsigned int and said, hey, it's okay, the mismatch is okay, do the conversion anyway. We didn't need to do this static cast. This is just explicitly doing what it already implicitly would have done. But we're doing this to avoid the compiler error. So we pass -1, we get a big ass value. But if we instead copy like that, okay, cool. We instead just value initialize y to be this guy. Oh, that's cool. So you can actually just delete a line by doing Control X anywhere in the line. Noted. And then what about Alt up? I can't do that because it's thinking Alt Shift because I have a 50% keyboard, 60%. And if we then assign, because if we assign the value, how do we do it? Well, there's no narrowing conversion here. A static cast to an int y. And in this case, we need x. We pass this big ass value, it counts, or it counts all the way up to whatever it can hold, and then it counts all the rest. But that act of going down, that one wraparound lost us one number, so we already counted one number off, so we only have 1 minus however much we had left, which means we count not up to 0, but to -1. Because if it was to 0, it means we would have counted all the way through, all the way from the top, or all the way to the top, and then up to 0, which means we went through the top from 0 to maximum, and then up from minimum to 0. So 0 to maximum, min to 0, is equal to 2 times however much memory either one has. So, yes, this is the reinterpretive stuff. And then if we go back and then say y is x, and actually, is this just fine? No. Okay, cool. So it's still pissed. Alright. So we can do static cast to an unsigned int x, and then we pass, or then we print y. We had this guy, x is assigned to be this guy, but through wraparound via reinterpretive conversion yields -1. Wraparound via reinterpretive conversion yields initial value because no data loss. Oh fuck! I'm getting tired again. I should have just locked in and did this earlier. Whew, okay. I need music. I think. No. Maybe not. I'll just lock it in. If I fall asleep, I'll fall asleep and then go hard tomorrow. But I want to try and commit. I just gonna sleep back and then shit. All right. Yes. So we're saying, hey, -5 to an unsigned int, which is some big ass number. But then convert that back to an int. We take that big ass number and we count up to half of it about, and then back up to whatever we've got, and we go back up to -5. Because we were -5 from the top, which means if we count up to the top, we get -5. Cool. Part of this, converting an unsigned value that is out of range of the signed value is technically undefined. Really? Oh. Because signed could use different binary representation than unsigned. Really? I don't remember what 2's complement is. Is that just how regular ass binary representation is? So just powers of 2 to the power of the something? To the 0, to the 1, to the 2? It's now well defined. Really? That's pretty recent. Because otherwise, if we did an unsigned that was out of range of the signed, how would that work? If we ended up storing the index of a giant array that was unsigned, and we had some sort of function that got the index of it, and it returned the same type, so an unsigned int, and we stored it as an int, not knowing that, then it would be implementation defined apparently, because allegedly it could use different binary representation, but I'm on C++ 20, yo. Oh, on the modern. Okay, because on the modern system, it already used 2's complement probably, just due to modern operating systems. Wait, so the conversion produces modulo wrapping. Signed arithmetic overflow, where we overcount. Specifically signed is undefined, really? Well, I mean, maybe apparently not, because it was working before. Because, I mean, we were passing a giant number to an integer, and it was yielding a value that we were able to predict. Lossy conversions, yes, so like a long to an int, a long to a short, a uint32 to a uint16, an int32 to an int16, an int to an int16, same shit as an int32 on my system at least. An int32 to a character, an int32 to a uint8t. A long double to a double to a float, a long double to a float. All of these. Yeah. Yeah, so 3 is okay technically. It may result in data loss. It just depends on what the value is. For 3, we're just dropping the trailing 0. But for 3.5, this is an example where you're actually losing something. And maybe if you want the value to keep those errors and rounding errors, maybe you don't actually even want to assign an integer to be the value from a double in this case. Or from a double to a float, yeah, because if you have significant precision and then you assign that value to a float, well, the float can lose it. Float, okay, yeah, double 1.2. This is okay because we're not using that amount of precision. But for this double, we do, because the float is only doing 6 decimals in this case, or at least 5 of precision. Yeah, if it's lost and it converts back, so like if we converted this big ass number and we passed it to a float, so we went from a double to a float, or a long double to a float, or a long double to a double, well, we lose precision, we lose accuracy, and it's probably the case that I was gonna say it's probably the case that the number fits, but could there be the case with a float where you lose precision and the number can't fit? No, because regardless, it'll wrap around. So if you pass a float a number that's too big, it'll probably, I don't know what it would do. Would it start counting from whatever the minimum value is? I don't know what the minimum value a float can have is. Is it a decimal? I don't know. It seems like probably negative something something whatever. I don't even know what the min or max of a float is. I think, isn't it dynamic? No, I guess not. I don't know. I don't know what those values are. But if we pass it and we lose it and we pass the value back, well, we've gone from a number to a less precise number back. Regardless of what happens, or if the value is too big to go back, shouldn't be too big. The conversion shouldn't be such that the initial value actually gets larger by subtracting. Because I'm thinking that if there's a rounding error, like in this case, it goes, well, I guess it's not. It just goes to 5.7. It just drops the rest off. It doesn't necessarily do a rounding error. So it seems like technically then, if you're just losing decimals, you're actually always getting a smaller value. So if we're getting a smaller value and it fits within range, it should be okay. But you're getting a value that's closer to 0, because if you had a negative number and then you had a more negative number that had extra decimals behind it that were non-zero, that weren't trailing zeros, and then we converted it, we would lose that extra. So we're actually, it's getting closer to 0, which means we're converting. It seems that, yeah, all long double values converted to a double and then back would fit within the long double, because they can't get bigger, they can't get out of range, they only get more in range, or closer to the center of the range, and then the long double would hold that value, but it would be a different value than it started with. Yes, different value. So we're static casting 3.5 to an int to get 3, but then we're casting 3 to be a double, and then we get 3.0. So we went from 3.5 to 3, or 1.25, 2, 3, 4, 5, 6, 7, 8, 9. And then we're converting that to a float, so we get like whatever, 1.23456, or something like that. And then go back to a double. Well, now it's 1.23456. Oh, it actually is a rounding error. 5, 6, 7, 8, 9 goes to 5, 7. Rounding error. Which means in this case, we actually did get a number that is bigger. My initial thoughts were correct. 5.7 is bigger than 5.6. So potentially we could have a number that's right on the line, the maximum that a float can hold, and then we convert it, and it actually gets a rounding error of a number that's too big, so then we end up getting a weird number. It should be fittable actually, because the wraparound would happen there. Something like that. Yeah, and then we convert it back. We don't get the same thing, because this is lossy. And again, lossy is may be lost. Just depends on what the data is. If the data is using all of that memory, we're going to lose that data, buddy. The difference of data between the two types. But if we're not using that data and we're only saying 5 inside a fucking long, a long int, yo, an LL, well then we're cool. We convert it back and forth, and and it never gets lost. Because 5 is holdable within like 4 bits. 3 bits maybe. What is it? 1 plus 2 is 4? Yeah, 3 bits. Yep, 3.0, not 3.5. Alright. When implicit lossy conversions are done. Okay, so if we do bump, narrowing conversion, buddy, data loss, womp. What runtime? So, oh, actually, let's do assignment. The narrowing conversion is only flagged because of brace operation, or brace initialization. Integer constant is too large. Constant too big. Oh, so that would have been so big that even an int64 can't hold. But in this case, we're doing truncation. So it seems like truncation is data loss. Whereas a narrowing conversion seems like it's the same, but it seems like narrowing conversions are when we're doing floats to integers. So when we're actually losing like a whole type of data, like the whole decimal is gone, compared to truncating, we're just losing pieces. What happens if we take a float x and then we assign it some big ass number like this? Yeah, truncation. So truncation is when the size is actually fully too large, but does this become a narrowing oops. Does this become a narrowing conversion if we... No. So truncation is... So it seems like narrowing conversion is just the conversion type. It's not that we're out of range of memory. It's that the data types are incompatible, meaning when we convert from this data type, we are warning you that any value, 1.1, 3.0, any of this shit going to an int, we are losing something. It's a narrowing conversion. And brace initialization will flag that. If we instead do assignment or copy initialization, so using the assignment operator, it's not a narrowing conversion to go from a long double to a double. It's truncation, because the act of the converting certain values, there's nothing that's lost. Our value isn't too big. It's not, there's this much memory for a float and there's this much memory allocated for a double, but if our value is only using the same amount of memory that a float would use or less, then the conversion is fine. There's no truncation and there's no narrowing conversion because we're going from a floating point value to a floating point value. If we go from floating point to integer, then by definition we are dropping the floating point. That's a narrowing conversion. So it's the type of data conversion as the issue by definition. But truncation is when the value is different. So the value is so large that we're going to lose pieces of it if we try and fit it in something else that's smaller. If the value is smaller, no issue. But when it's too big and we are cutting it off and getting errors because of it, or rounding errors, that is truncation. Okay. I thought they were different. I just didn't have it spelled out. Look it up. Into a double is typically a safe conversion because an int is 4 bytes and a double is usually 8 bytes. And on all systems, all possible int values can be represented. However, There are some architectures where they are both, and on some, an int to a double is a lossy conversion. Really, an int to a double? Meaning, so an integer to a floating point value, and it just happens to be a double. So if we have this big ass double, oh, we're casting a long, wait, an int to a double? Yo? Int to double is lossy? Oh, if there's an architecture where an integer and a double are 8 bytes, then a long, well, isn't a long already bigger than a double? A double is 8 bytes, sure, but if an integer is 4, and a long is 8, and a long is 16, then a long to a fucking double anyways is a lossy. There's this big ass number, and it's going to be floating point, but the floating point can't hold a number that's that big. So we get data loss, which means truncation, which then means we have the smaller floating point value, which is then put back into a long, which fits. But that is not the value that we started with. So this here yields truncation, and then this yields, it's just the final result of it's the reversal of a lossy conversion. Yeah, see, a long 64 bit. Oh wait, yeah, because wait, it at least 8. So if it's at least 8, then there are architectures where it's probably bigger than 8, which means that going to a double is actually losing value. And assuming that a double can't hold the same amount of integers as, or assuming that a double is restricted to be smaller than an integer, meaning not as positive and not as negative, because it has to have some memory allocated to the decimal points, which means it can't be as large, because, like, let's say 1,000 is the limit for a long, or just a fucking long, whatever, something, an 8-byte integer. Well, 1,000 point other stuff would take up more memory by definition. We have more bits in this representation, in this piece of data, which means the values can't be as high or as low. That way we have room. So maybe it's only 700 point something to whatever, 7 or 6 bits of precision. Which means if your int and your double are the same, actually going from an int to a double is a lossy conversion, because the int actually stores more. So it's basically just saying that, hey, there are architectures where an int stores higher and lower values than a floating point value, or than a double at least. So not only a float, but a double. Unsafe conversions should be avoided. Yeah, we just want to make this shit predictable. When they are used, it's most often when constrained values to be converted to those that can be converted to equal values. Oh yeah, because we're talking about unsafe, meaning, so there's lossy. We probably don't really want to do lossy, but reinterpretive, not necessarily an issue. Like, we could convert -1 to this big ass number for an array index, and then take that and then store it back and say, hey, what did we use to access the array index? Oh, we did -1, because it converted back and overflowed back, modulo wrapped back to -1, back to the minimum, and then counted all the way up because we had extra. I don't mind that some data is, or hold on, here we go. We can guarantee that the int is non-negative, then it's okay to convert. There's no issue here. Yeah, because the unsigned int holds the value anyway. So if the data is okay, then we're cool. But if we don't know, then probably best to avoid that. And luckily, like, standard character input can tell whenever there's overflow happening, so we should be protected by using standard character input and doing a check for the user. So if extraction fails, then, well, the user entered a value that's too damn big or small. It's out of range. Into a bool is loss related, but okay, here we go. So this is separate. We don't mind that some data is lost because it's not always relevant. Meaning, some data, meaning we are content with some data being lost on occasion when that data isn't relevant. This should say when it is not relevant. For example, converting it into a bool. So if we take 50 and we convert it to a bool, well, anything that's non-zero in a bool gets converted to true, which is 1. So 3, 2, 1, 1.4. It seems like anything that's greater than 1 probably. We're converting it to an integer. Gets converted down to 1. But if it's less than 1, or maybe if it's just non-zero, I don't know what happens if it's a negative 1. It's converted to 0, so it's okay, there's no difference. Typically okay with this because we're just checking if the value has, if the int has value 0 or not. So we could say if an integer, and it basically just says, or we could say if not an integer, meaning if the integer is 0. Because the integer returns 0 only if it is 0, I think. In all cases, if we convert a type whose range doesn't support, it's probably unexpected. Meaning, an integer, which is way too big to a character, we get some wacky shit. There's data loss here. Why? Because an integer is at least like 2 or 3 bits, but in this case probably 4. Character's only 1. We're losing data, buddy. At least in this case, where our value is out of range. So yeah, don't pass shit that's out of range unless you're totally ready to handle it and you're good to go. Probably just don't do it. Basically just don't put a fucking fork in the damn electrical socket. Yes, overflow, it goes 48, and then we pass 48 back to an integer, and we go from 30,000 to 48. Overflow is well defined for undefined, or for unsigned, and is undefined for signed values. Okie dokie. Apparently, allegedly. Converting from a larger integral to or floating to a smaller. Well, yeah, because fucking 0.1234 fits within a float's precision, and 2 fits within a short that goes up to, I don't know, like 63 or something, or 64 maybe. Ow, I think I was like pressing my foot on the ground hard and it got warm. Expected result. Yeah. Some rounding loss if there's a loss of precision of the smaller type, meaning that we pass something to the smaller type. Oh, meaning if we do it, it could fit, but then still be a loss of precision? Meaning it has enough memory, well, it has enough memory to hold the value, so like it can hold up to 17. So if we passed it 16 point something, and it ends up losing precision and rounds up to 17, then sure, it might be able to fit it, but maybe the precision is fucked up. So the bounds, it can hold higher and lower values, but not to the same precision. Yeah, so like if we passed from a double to a float, and we passed in fucking 16.12345678910, well, and we had a float, the float would be 16 point something. It can actually hold huge numbers. It could go all the way up to thousands and shit. But it's not going to stay the same precision, so there might be data loss, yo. Wait, this is just standard data loss, bro. We're passing a double to a float. It's data loss. But then if we do set precision of f, it's going to be inaccurate. Yes, we see a loss of precision. Duh! What the fuck is the point of this? Oh, these are just like rehashing the shit that we already talked about. An integer to a floating is probably okay as long as it fits. Yeah, but if we have an architecture where it doesn't fit, or we're just using types that don't fit, like a fucking integer to like a mini float, if that's even a thing, or a long to a double, or a long to a float, well, we're fucked because it's too big. If we pass in a value that's too large out of range. Basically, you pass shit that's out of range, you might get wacky results, especially if it involves data loss. Yeah. From a float to an integer, and again, we lose the fractional, so there might not necessarily be data loss, like 500.0 converted to 500. Well, there's no data loss. Maybe it's the same amount of memory, 4 bytes in a float or 4 bytes in an integer. Okay, maybe we're cool here. And we're not at a range, so maybe it's a double to an int. Okay, sure. There's a narrowing conversion because we're losing, through brace initialization, we're losing the decimal. But maybe the value is still cool because an int can 100% hold 400. So it could be okay. Just depends on what the float value is. If we're passing fractional shit, like from 0 point some or from 0.0 up to 1, well, integers assigned to those values are only ever going to say 0 or 1. It's probably not good to pass opacity values to an integer. Cool. Narrowing conversions, baby. Alright, I will continue this tomorrow. Because I'm tired for some reason. Well, I think I'm still suffering from sleep debt, so I'm going to go to sleep in a second here. And then I'll just continue tomorrow. Sorry, only 50 minutes today, but sometimes it is what it is. It shouldn't be. I'm working on it. But, yeah.